talk about symmetry. So some graphs can display certain kinds of symmetry. We have symmetry about the y-axis, which is when the y-axis acts like a mirror, or if you were to fold the paper on the y-axis, the two halves would lie on top of each other. There is symmetry about the x-axis. The x-axis acts like the mirror, or the place where you should fold so that you have the two pieces lying on top of each other. And symmetric about the origin, the mirror is hard to visualize, but you can see it as two folds. If you fold over the x-axis and then over the y-axis, so it's like you're folding this grid into quarters, then this top piece will lie on top of the bottom piece. So those are the three kinds of symmetry that we're going to be looking for. There are certainly other kinds, but these are sort of common ones that are useful to be able to recognize. So looking at them in a picture, it's quite easy to recognize that they have symmetry. But if we only have the equation and not the picture, so this or this or this, then we want to be able to look at that and tell whether or not the graph will have symmetry without having to draw the whole graph. So these are the tests for symmetry, and it's just a little summary, and they all come from this picture. Okay, sort of the definition of symmetry is what we use to create the tests for symmetry. So if this is my original point right here, x comma y, the point that is symmetric to that point about the y-axis is over here. And those 2 points go the same distance away from the origin. One of them goes right and one of them goes left. So one goes positive x, the other goes negative x, and then they have the same y because they both go up the same amount. So in this case, if you replace x with a negative x, shouldn't make any difference. Both of those points, if the graph is symmetric to the y-axis, both of those points will be on the graph. So if you replace an x with a negative x, shouldn't make any difference. Now with x-axis symmetry, if this point is on your graph, then so is this point. And those 2 points have the same x coordinate because they go over the same amount from the origin, but then one goes up and one goes down. Same distance, just different directions. So this one would be x comma y, this one would be x comma negative y. So if you were to replace a y with a negative y in a function that has, right, in an equation that has x-axis symmetry, it shouldn't make any difference. Y with negative y shouldn't make any difference. You'd still be on the graph. And then for origin symmetry, if x comma y is on the graph, then do your 2 folds. This point would be x comma negative y. Fold it again, and you'd have negative x, negative y. So if you were to replace the x with a negative x and the y with a negative y, shouldn't make any difference. Both points should be on the graph. So those are my tests. If you replace, to test for y-axis symmetry, replace x with negative x. And if your equation remains unchanged, then you know you have y-axis symmetry. For x-axis symmetry, you place y with negative y. And if the equation is unchanged, you have x-axis symmetry. And then for origin, replace x with negative x and y with negative y. And if the equation is unchanged, you have origin symmetry. So I'll do an example of each. So here's y equals the absolute value of x. I can graph it and say, oh yeah, that has y-axis symmetry. I'm going to show it has y-axis symmetry with the algebraic test, okay, in case I didn't have a graph to look at. So I'll start by writing down the original equation. And then in the original equation, replace x with negative x. Y equals the absolute value of negative x. But what is the absolute value of negative x equal to? X, which is the same thing as the absolute value of x, right? The absolute value of negative x and the absolute value of x are the exact same value. So what happened is I replaced my x with a negative x and found that my equation was unchanged. Because I got the exact same equation, I have y-axis symmetry. Okay, I'm going to make one up off the top of my head. It's not in your notes. I want you to test y equals x cubed plus x squared for y-axis symmetry. So I've got my original equation. The y-axis symmetry test replaces x with negative x. So this will be y equals negative x cubed plus negative x squared. So remember, I'm replacing x with negative x, so I'm cubing negative x. I'm cubing that whole thing, so I put parentheses around it. And negative x cubed, that means negative x times negative x times negative x. So what's that going to come out as? Negative x cubed. So it's an important distinction, the difference between this guy and this guy. Negative x quantity cubed means negative x times negative x times negative x. Negative x cubed means negative x times x times x. So if there's no parentheses, the negative doesn't belong with the x. It just belongs in front. All right, and then negative x quantity squared, that means negative x times negative x, which is what? Positive x squared. Okay, so in my equation, I replaced x with negative x and y with negative y. Are these two the same? No, not the same. So I do not have y-axis symmetry. Those three little dots mean therefore, by the way. All right, so let's test one for x-axis symmetry. My equation is y squared equals x. If I'm testing for x-axis symmetry, we replace the y's with negative y's. So instead of squaring y, I'm going to square a negative y. And negative y quantity squared, what is that? Positive y squared. Exact same equation, right? So I do have x-axis symmetry. Okay with that? Any questions? All right. So now I'll show you the one for origin. We have a y equals x cubed. We graph it. You see it definitely looks like it has origin symmetry. We're going to prove it with the algebraic test. Okay, so I have, write down the original, y equals x cubed. Replace the y with a negative y and the x with a negative x. So the test for origin symmetry, you replace both of them. So negative y, I can drop the parentheses, that's just negative y. Negative x quantity cubed means negative x times negative x times negative x, which is negative x cubed. Is that equation that I just wrote there equivalent to the original? Yeah, it looks different, but it actually is equivalent to the original. So yeah, if I divide both sides by -1, I get y equals x cubed. Same as the original. You can also think of it as add y to both sides, add x cubed to both sides. And you would end up with x cubed equals y, which is equivalent to y equals x cubed. So these are the same. Therefore, I have origin symmetry. So sometimes after you make your replacements and simplify, sometimes you can do a small manipulation to try to turn it into the original. So you have to see that it's equivalent. Sometimes there's no manipulation in the world that will make them look the same. So then you just say the symmetry doesn't exist. All right. So here I have 3 equations. For each of them, I want you to do the 3 tests and determine what kind of symmetry or symmetries it exhibits. All right, so we'll look at this first equation, x equals y to the 4th minus y squared. We want to test for symmetry about the y-axis, which means replace x with negative x. So this becomes negative x equals y to the 4th minus y squared. Now, right now, it does not look like the original equation, right? Is there anything I can do to it? Any legal equation manipulation I can do to make it look like the original? No. I could try, right? I could say, well, the problem is that this is a positive x and I have a negative x. I could try to fix it by multiplying both sides by -1. But when I do that, my x gets fixed, but then both the signs on my y's get changed, and it still doesn't look like the original. So there's nothing I can do. We say that one does not have y-axis symmetry. But for the next one, when I replace the x's with negative x's, negative x quantity squared, that means negative x times negative x becomes positive x squared. Because negative times a negative is a positive. And the absolute value of negative x is the same thing as the absolute value of positive x. They're the same number. So I do have my original equation back. Now I have symmetry. How about the third one? Do I get symmetry? No, no y-axis symmetry for the third one. All right, x-axis symmetry. Which one had it? The first one. Okay, let's look. Y to the 4th minus y squared. Okay, and for x-axis symmetry, we replace y with negative y. So I get x equals negative y to the 4th minus negative y squared. Negative y to the 4th, it's an even power, so I'm going to have 4 negatives multiplied together. The answer will be positive. So I get x equals y to the 4th. And negative y squared, that's negative y times negative y, which is positive y squared. Same as the original. And then the other two come out as no symmetry. Sure, yeah. X squared y squared plus xy equals 1. Okay, so I am just replacing y's with negative y's. So I've got x squared times negative y squared plus x times negative y equals 1. Now the negative y squared will turn back into a y squared, because that means negative y times negative y. So this becomes x squared y squared. But x times negative y, positive times a negative is negative, so I get minus xy equals 1. And this is different than my original by 1 sign. Right? This negative sign makes it different than my original equation. Yep. And in the last one, anybody get symmetry for it? I showed you, yeah. The last equation has origin symmetry. So my original equation is x squared y squared plus xy equals 1. And for origin symmetry, to test, you replace the x's with negative x's and the y's with negative y's. So we have negative x squared times negative y squared plus negative x times negative y equals 1. Now the negative x squared and the negative y squared are going to just become positive x squared and y squared. And what is negative x times negative y? Positive xy. Negative times negative is a positive. So this is plus xy equals 1. And that is my original equation. So I have origin symmetry for that one. And not for the other two equations. Okay? All right. I'm not going to do that. Okay, so finally, you should be able to complete your graph if you know something about its symmetry. So both of these graphs, I've only drawn half of it, and I'm telling you that it has a certain kind of symmetry. So in this first one, it's got y-axis symmetry. So if you're good at visualizing things, you could just kind of sketch it out, treating the y-axis as a mirror. So you'd have like this, 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 like that. Okay. But that is, so you're welcome to do it that way, totally fine. That's easier for some people than it is for others to be able to visualize what the other side is going to look like. So if you find that difficult, little trick is use the definition of symmetry, right? So pick out a few key points. So this one's 0, 3. This one is 2, 1. This one's 2, negative 1, 3, negative 1, and 5, 1. And y-axis symmetry, the test was replace x with negative x. That's what you do here. Replace the x coordinate with the opposite of the x coordinate. So 0, 3, what is the opposite of 0? Still 0. So that point stays the same. And 2, 1, the opposite of 2 is negative 2. So we go to negative 2, 1. 2, negative 1, we go negative 2, negative 1. 3, negative 1 becomes negative 3, negative 1. And 5, 1 becomes negative 5, 1. And then you just connect them in the order that you drew them. Now with symmetry about the origin, that one's even harder to visualize. Some people can do it. I can't do it. So I always do the point thing with origin symmetry. So again, we label some points. And then the test for origin symmetry was replace x with negative x and y with negative y. Do that here. Replace the x coordinate with the opposite of x and the y coordinate with the opposite of y. So 0, 3, what's that going to become? 0, negative 3. And 2, 1 becomes negative 2, negative 1. 2, negative 1, where will that go? Close. You're halfway there. So the opposite of 2 is a negative 2. What's the opposite of negative 1? 1. So we're going to go negative 2, 1. This is going to become negative 3, 1. And 5, 1 becomes negative 5, negative 1. And so Origin symmetry can also be described as a rotation, 180 degrees around the origin. So that's one way to visualize it. We just took this guy and whoosh, swung it around. So you guys feel comfortable with the 3 kinds of symmetry? All right. So for the remainder of class, we're going to play with the graphing calculators. So does everybody have one? We'll graph things. Yeah. Okay. So I have a few in my office. I'll go run down and get them so that people can practice. So to find 2 cubed, there is no little cubed button, so we would have to do it with the caret button. 2 caret 3. All right. So now we're going to hit clear because hit it 2 or 3 times because we're neurotic about having a nice clean home screen. All right, so to find the square root of a number, so square root is a second function. It's right above the x squared key. So you would press second, the x squared key, and then put in 9. Close the parentheses. So the parentheses are telling the calculator what to take the square root of. So whatever's in parentheses, it will square root. So you hit enter, you get 3. To find a cube root, that's actually in the math menu. So we're going over a lot of stuff right now, where stuff is. You'll have this as a reference while you're getting used to it, but the things you use a lot, you'll start to remember where they are. So you press the math button. Option 4 is cube root, and option 5 is to take a root, any root you want, the 4th root or the 5th root or the 6th root. So right now we're just doing a cube root, so I'm going to choose option 4 and put in 8. Close the parentheses. And it tells me 2. The other way to do it, just like with squaring, there's a special button, but there's also the general button. I'm going to do it the general way. So if I want to take a cube root, I would type 3 first, 3 for cube root. Then go to the math menu and choose option 5, the xth root. And then type in parentheses 8 and hit enter, and it will give you the cube root also. Mm-hmm. Mm-hmm. Yes. And then it pops up in your home screen, and then you just type in the number that you want the cube root of. In parentheses, yeah. Yes, you could. The cube root of 8 is the same thing as 8 to the 1/3. So you could do 8 caret, and you just have to put the 1/3 in parentheses because the order of operations would tell, if you didn't have parentheses there, it would say do 8 to the 1st, which is 8, and then divide by 3. So we put parentheses around the 1/3 for the exponent. It's the same thing. Good. Okay, so if we want, there's also an absolute value button in here. So if you go to the math menu, see how there are menus across the top? There's math, number, CPX, and probability. You want to go into the number one, number. And the first option is ABS for absolute value. Now, the older models, when you click this, it's just going to pop up ABS parentheses, and it's saying, what do you want to take the absolute value of? Right? Newer models, you'll actually get absolute value bars, and you type in what you want to take the absolute value of. So if I want the absolute value of -4, type that in, hit enter, and you get 4. Okay, so what is 1/2 plus 1/3? By hand, in your head. Close. 5, 6. Yep. 3 over 6 plus 2 over 6 would be 5 over 6. So let's see, I want to do 1 half plus 1 third. The division key, because fraction bars really are just mean division. So I just use the division symbol to get fractions. So I have 1 divided by 2 plus 1 divided by 3. Press enter. Now, how do I know if that's 5/6? Yes. Yep, I could do math. The first option changes your answer to a fraction. So you hit enter, enter, and it gives 5/6. So decimal to fraction is a really convenient button to know. All right, so now I'm going to use that second answer thing. So let's hit 4 plus 5. 4 plus 5, enter. And then you go, oh, I really want the square root of that. And instead of having to retype the 9, I can hit square root. And then I can have the calculator plug in the previous answer, the last answer I got. So you hit second answer, which is right above the negative sign. It's the second function of the negative sign. So the square root of the previous answer, and I get 3, because my previous answer was a 9. So that's another handy one for like when you're doing the quadratic formula. You can figure out what's under the radical, then hit, oh yeah, square root that. So in fact, here's a good one to try. We want to do -7 plus the square root of 7 squared minus 4 times 1 times 12. And -7 minus the square root of 7 squared minus 4 times 1 times 12. So I can do this by using my second entry key. So I could do -7 plus the square root. Just press clear. Yep. So it's right in the upper right area. You can clear everything if you want. So -7 plus the square root of 7 squared minus 4 times 1 times 12. Enter. And we get -6. But then I want to do the same thing, exact same thing again, but I want to put a minus sign right here. That's what we'd have to do for the quadratic formula. So you hit second entry, pulls up the last thing you typed, use your arrow key, change the plus to a minus, and hit enter. -8. All right, so you do have to be careful with division problems. Sometimes you need to use parentheses on the calculator, even when they're not written. So 10 divided by 2 plus 3, in your head, what should that come out to? 2, yeah, because we have imaginary parentheses around the top and bottom of a fraction. So you add the 2 and the 3, you get 5. 10 divided by 5 is 2. But if I type it in like that, 10 divided by 2 plus 3, I get 8, because what did the calculator do? Yeah, the order of operations says to do this division first. 10 divided by 2 is 5, then add 3 and you get 8. So you have to tell the calculator, no, I mean do the 2 plus 3 first by putting it in parentheses. Okay, we're going to skip this. All right, so the graphing capabilities, so we've done sort of like arithmetic capabilities. Your calculator can also graph equations. So to get it to do that, go to the y equals button. It's upper left, go to y equals. If there's anything written there, just press clear to get rid of it. Along the top, you'll see plot 1, plot 2, plot 3. None of those should be highlighted. Okay, if they are, just put the cursor on it and press enter. So I just turned plot 1 on. I just highlighted it. I'm going to turn it back off. Now we're going to type the equation x cubed. So the x button is right here next to alpha. It says x, t, theta, n. So those are just the common variable names. So use that for x. Caret cubed minus 3x caret squared plus 2. So this is going to look much more complicated than the things we just recently graphed by hand. All right, so now we have to decide where in the coordinate plane, which is infinite, right? The x-axis goes forever to the left and forever to the right, and the y-axis goes forever down and forever up. We only have this little, what, like 2-inch by 3-inch screen that we can look at different spots in the plane. So we have to decide where in the coordinate plane we want to look. And you get that by using the window. So the window says where in the plane you want to look. So you give it the smallest x and the biggest x, the smallest y and the biggest y. So a good place to start is generally -10 to 10, -10 to 10. And you can always leave, you can just leave x scale and y scale at 1. I never change them. So once your window looks like this, press graph. And we get a picture. Graph is the upper rightmost key. So we have a graph. So we can zoom in. Let's say what we're really interested in is where it crosses the x-axis right here. Okay. So you can press the zoom button. And the first option is zoom box. It's my favorite way to zoom because you have the most control. Hit zoom box. And you get a little cursor is blinking in the screen. Use your arrows to move it. And we're going to create a box around our point of interest, whatever that point of interest might be. So I'm going to create a box right around this x-intercept. And the way you do it is put the cursor where you want the upper left corner of the box to be. Then you just press enter. And then you can go down and over to create a box. And then my calculator is going to zoom in on this part of my graph once I press enter again. No, it doesn't ever show the numbers. The screen's just too small to fit those things in. What you can do is you can press the trace button, and then it gives you the coordinates of wherever the cursor is on the bottom of the screen. And then you can move the cursor along the graph using your arrow keys. Okay, so here's my original graph in the window I started with. Go to zoom, choose option 1, zoom box, and you'll have a cursor blinking in the center of your screen. Use your arrow keys to move it so that it's going to sit where in the upper left corner of a box that you're going to draw. So I want to draw a box around this x-intercept. So I move the cursor to here, then you press enter. Then you can use the down key and the right arrow key to create a box. Once you have your box, press enter, and it will zoom in on that area. So something that you can do once you're here, if you're interested, is click window and it'll tell you what the smallest x and the biggest x and the smallest y and the biggest y are in this new window that it zoomed in on for you. So it's just if you're curious, if you want to know, you can find out. All right. Move to number 9. So to graph an equation on the calculator, the equation has to be in the form y equals something with x's. So if I have xy equals 5 is the equation I want to graph, how would I enter that in the calculator? Close. 5 divided by x, because this is multiplication right here, x times y. So to get y by itself, divide both sides by x. So you would enter y equals 5 over x. So let's graph that. 5 over x. So I just cleared what was there. Just have the cursor there, press clear. 5 over x. And then let's use a standard window, the negative 10 to 10, negative 10 to 10. I could type it in, negative 10, enter 10, enter, negative 10. But because we use this window so frequently, there's a shortcut to get this window, which is zoom option 6, which is the standard viewing window, negative 10 to 10, negative 10 to 10. And there's our graph of 5 over x. All right, so what if I want to graph x squared plus y squared equals 9? How would I enter that in the calculator? Squared, yep. So, yep, subtract x squared from both sides. So you get y squared equals 9 minus x squared. Then square root both sides, right? So I get y equals plus or minus the square root of 9 minus x squared. Because there are two things that when I square them will give me 9 minus x squared. The positive square root and the negative square root. So I actually have two equations. So I'm going to put y1 is the square root of 9 minus x squared, and y2 is going to be negative the square root of 9 minus x squared. So I'm going to have to, because of the plus or minus, I have to write two different equations to represent this single x squared plus y squared equals 9. So go back to y equals, press clear, type square root of 9 minus x squared, close parentheses, and then the negative, and I'll put square root 9 minus x squared. I can zoom 6 to get a standard window. And this is supposed to look like a circle. Why does it look like an egg? Yeah. Why are they different scales? Okay, so in the window, I entered negative 10 to 10, negative 10 to 10 for x and for y. My x scale and my y scale is 1. That just means that every tick mark represents 1 unit. So x goes from negative 10 to 10, y goes negative 10 to 10, Why is my shape coming out distorted? Yeah. Yeah, the screen is wider than it is tall. So we have 20 units of distance along x, right? -10 to 10. And 20 units of distance along y squished into a smaller space. So it's squishing my circle. So the way to fix it is in the zoom menu. There's an option called zoom square, and it will make the distance between tick marks equal on the both axes. So you hit enter, and now it looks more like a circle. So finding a good window that shows all the important features of your graph and without having too much empty space, right? Like I have all this empty space here. So that means I'm going to lose some detail because this is so small. And so finding a good window is really kind of an art, and it will take practice to get good at it. And it's always a little bit of trial and error. So you're going to have to start with a guess, whether it's -10 to 10, -10 to 10, or you might have some other guess if your equation represents a real life thing, right? If x is representing time, you might go you might start at 0, right, instead of looking at negatives. Okay, so we skipped some stuff here that I'm going to let you play around with now on your own. So start up here at E with 3E, where they're estimating the intercepts, the x and y intercepts of this graph.